students, welcome back to motion in straight line. If a particle covers delta x displacement in a very short interval of time delta t, then what is the velocity of that particle at a particular instant t? Then we use a mathematical tool, as we said, differential calculus. That is, if a particle covers delta x displacement in delta t time, then the instantaneous velocity of that particle can be calculated as instantaneous velocity v is equal to dx by dt. It's a very important relation. Instantaneous velocity is the first derivative of displacement with respect to time. First derivative of displacement means if x is a function of time, if x is a function of time, like x is equal to at square plus bt plus c, where a, b and c are constants. If we are going to put a value of t is equal to 1, then instead of t we can use 1, then we get one answer. If this changes, t changes, position also changes. Instantaneous means it depends upon the change with respect to time. What is the velocity of the particle which is related to this equation at square plus bt plus c? We can use this method. V is equal to dx by dt. So instantaneous velocity v is equal to dx by dt. Just to use the value or the equation of x here, we can write it as d by dt of it's an operator in mathematics. Differentiation is a process. So d by dt of at square plus bt plus c. Just to use the value there. The next procedure is, this can be written as d by dt of at square plus d by dt of bt plus d by dt of c. D by dt of at square, d by dt of bt plus d by dt of c. Just split the operator to three different terms. After splitting that one, we think about a major rule of differentiation, like d by dt of k into t raised to n. If there is a function just like this, d by dt of k t raised to n, k is a constant, then this is equal to k into, we can take k outside, k into d by dt of t raised to n, and this is equal to k into n t raised to n minus 1. For example, if d by dt of 100 t raised to 5 is going to be differentiated, then this is equal to 100 into d by dt of t raised to 5. D by dt of t raised to 5. Okay. And this is equal to 100 into, the power of t is 5 here, therefore 5 into t raised to 5 minus 1. Using this rule, n t raised to n minus 1. T raised to 5 is 5 t raised to 5 minus 1. Clear? That is equal to 500 t raised to 4. This rule is used to solve that type of question. Okay. By using that method, we can find out the instantaneous velocity of the particle. You remember this equation? We write this equation like velocity, instantaneous velocity is equal to d by dt of at square plus d by dt of bt plus d by dt of c. A is constant, b and c are constants. Okay. So the first step is put a outside the operator, a into d by dt of t square plus b into d by dt of t plus 0. Why? Because differential of a constant is equal to 0. Another rule is there. D by dt of a constant is equal to 0. So a into d by dt of t square plus b into d by dt of t plus 0. And this is equal to a into d by dt of t square is 2t raised to 2 minus 1 plus b into d by dt of t is 1 t raised to 1 minus 1. 1 t raised to 1 minus 1. Okay, t means t raised to 1. Therefore, 1 t raised to 1 minus 1. That is equal to 2at. 2at t raised to 2 minus 1 is equal to t raised to 1. That is 2at plus b. 2at plus b meter per second is the instantaneous velocity of that object. That means we have the initial equation for displacement as x of t is equal to at square plus bt plus c as a function of time. What is the velocity of the particle at any instant when we can use differential calculus? Using differential calculus, instantaneous velocity is equal to dx by dt. And use the value or the equation of x there, d by dt is considered as an operator. D by dt of that equation, at square plus bt plus c. Then we can use the rules. Which rule? D by dt of k t raised to n is equal to k into n t raised to n minus 1. Then we can write that equation like this. D by dt of a constant is equal to 0, and finally we get the answer 2at plus b meter per second. This is the instantaneous velocity or the method to calculate the instantaneous velocity of an object. Our next point is acceleration. Rate of change of velocity is acceleration. Velocity is a vector quantity, therefore acceleration is also a vector quantity. Instantaneous acceleration is a is equal to dv by dt. A is equal to dv by dt. So we can write the equation of acceleration as acceleration a is equal to change in velocity by change in time. It is a vector quantity. Dimensions of acceleration are, dimension of velocity is lt raised to minus 1 by t is equal to lt raised to minus 2. And the unit of acceleration is meter per second square. Acceleration, rate of change of velocity. Instantaneous acceleration a is equal to dv by dt. First derivative of velocity with respect to time gives acceleration. Okay. Now we have the topic velocity time graph. We already discussed in class 9 the position line graph of different objects. Now we have the importance of velocity time graph. If an object is moving with the uniform velocity, then the graph is a straight line which is parallel to x-axis. There is no change in velocity with respect to time. Look to this graph, velocity time graph, the change in velocity with respect, there is no change in velocity. The velocity of the particle is constant or uniform velocity. Therefore, the acceleration of this particle in this case is equal to 0. Okay. there is no acceleration. Rate of change of velocity is acceleration. There is no change in velocity. Velocity is constant and the graph is parallel to x-axis. Okay. The second one is the velocity of the particle changes. Particle changes uniformly. We have a line with a positive slope and it makes an angle theta here. This theta is called the slope of the graph. This angle theta is called the slope of the graph. Slope of the graph is tan theta. Tan theta is equal to change in velocity by change in time. Opposite side by adjacent side. So tan theta is equal to delta v by delta t, and delta v by delta t is what? Delta t by delta t is acceleration. Change in velocity by change in time is acceleration. So slope of velocity time graph gives acceleration of an object. It is clear that it is moving with a positive acceleration. The velocity increases uniformly with respect to time, therefore it has a positive acceleration. To look at this graph, initial velocity is not zero here. Velocity decreases with respect to time. Therefore, we have a line with a negative slope. If you take the slope of that one here, then if you are going to take tan theta is equal to, again, the same equation, opposite side delta v by adjacent side delta t. We get deceleration of the object, decelerating or retarding. Velocity decreases with respect to time. Now, another use of velocity time graph is to find the displacement of the object. We can use velocity time graph to find out the displacement of the object. The slope of the graph gives acceleration or deceleration, depends upon the nature of the line. If you take the area under a velocity time graph, we get displacement of the object. So here we have a velocity time graph. Velocity time graph means this is accelerating. No acceleration, deceleration like that. The another purpose of this graph is we can find out the displacement by taking the area enclosed or area under the graph. Area under the graph means we can see three different lines here. Area of this one is, this can be taken as O, the origin of this coordinate system. And we can divide. Different methods are there to find out the area. One method is explained here. We can construct a triangle one, another one a rectangle, and this is third one another right angle triangle. Displacement covered by the object is, displacement is equal to area of the triangle 1 plus area of this rectangle 2 plus area of the last triangle 3. So displacement of an object is the area under velocity time graph. Slope of velocity time graph gives acceleration or deceleration. The area under velocity time graph is displacement. Okay. With the help of velocity time graph, we can derive the kinematic equations, the well-known equations. V is equal to u plus at, s is equal to ut plus half at square, v square is equal to u square plus 2as. They are velocity time relation, position time relation, position velocity relation. We can find out or derive these relations on the basis of velocity time graph. This graph says that velocity time graph is here. The initial velocity of the particle is non-zero. It starts with the initial velocity u, moving with the velocity v, and the final velocity of the particle is taken as v. Initial velocity is u, final velocity is v. after a time t. After a time t, it has a final velocity v. Initially, it is moving with an initial velocity u. And the first one is the velocity time relation, independent of the position of displacement. To find out the velocity time relation, we can see a triangle here. A rectangle triangle ABC is here. Using this triangle ABC, you can take the slope of this graph. You can take the slope like tan theta is the slope of the equation. The slope of the equation tan theta is equal to opposite side of BC by the adjacent side is AC. So tan theta is equal to BC by AC. Tan theta is equal to BC is V minus U. V minus U. Change in velocity by, this is T. The adjacent side is T. So tan theta is equal to V minus U by T. Tan theta is acceleration, right? Tan theta, slope of the velocity time graph is acceleration. So acceleration A is equal to V minus U by T. By cross multiplying this relation, we get V minus U is equal to AT. That is, V is equal to U plus AT. If the object is moving with an initial velocity U and after a time t, it has a final velocity V is equal to U plus AT. If U is equal to 0, we can simply write this equation like velocity, final velocity is equal to acceleration. If the object is starting from rest, then U can be taken as 0. Then we can rewrite the equation like V is equal to AT. If it has an initial velocity U, the equation is V is equal to U plus AT. This relation is velocity time relation. As we know, the area under velocity time graph is displacement. Slope of velocity time graph is acceleration and this one is displacement area. To find out the position time relation, second one is position time relation. The distance traveled or displacement of the object after a time t. The final equation is independent of velocity, depends on time. Position time relation. So we can take the area of OABD equals, we can see a trapezium OABD here. So OABD, the area of OABD is half into sum of parallel sides. This is the sum of parallel sides OA plus BD, sum of parallel sides into perpendicular distance. So area of OABD is equal to half into sum of parallel sides into perpendicular distance. Sum of parallel sides into perpendicular distance. That is equal to half into sum of parallel sides is OA plus BD. OA plus BD into perpendicular distance. Perpendicular distance is AC or OD. We can take AC. Half into OA plus BD into AC. That is equal to half into OA plus BD into AC. OA is U, initial velocity U, plus BD is V, final velocity V, into perpendicular distance is time t. We can rewrite half into U plus V into t. And now we are going to replace this one. V must be replaced. Then we get the position time relation. That is, area under velocity time graph is displacement, and displacement S is equal to, we have the equation there, half into U plus V into t. Now we are going to replace U. We are going to replace U according to the relation, but we know V is equal to U plus AT. V is equal to U plus AT. Therefore, S is equal to, displacement S is equal to half into U plus AT into T. This is equal to half into 2u. U plus u is 2u. 2u plus at into t. Then open this bracket. We get s is equal to half into 2ut plus half into a t square. T into t is t square. We can cancel 1 by 2 and 2. We get displacement s is equal to ut plus half a t square. This relation is independent of final velocity v. So this relation is position time relation. S is equal to ut plus half a t square. Then we have the relation between position and velocity. Position velocity relation. The relation is v square is equal to u square plus 2as. Again we can take the area of that trapezium OABD. Area of the trapezium OABD is equal to half into OA plus BD into AC. OA plus BD into AC. And this is equal to half into U plus V into T. This relation is position velocity. So the final equation must be independent of time. So we are going to remove the time or replace the time with the relation, but here we are going to remove this one or replace this one, t. But we know the relation v is equal to u plus at again. At is equal to v minus u. T is equal to v minus u by a. We can use t is equal to v minus u by a here. We get s is equal to, we get area s is equal to area of trapezium OABD, area of velocity graph is displacement s is equal to half into u plus v, half into u plus v into v minus u by a, v minus u by a. S is equal to, this is numerator is v plus u into v minus u, a plus b into a minus b is a square minus b square. Therefore s is equal to v square minus u square. The denominator is 2a, 2 into a. Numerator is a square minus b square format. So v square minus u square by 2a. V square minus u square is equal to 2as, or v square is equal to u square plus 2as. This relation is velocity, position velocity relation. Okay.